Good day. My name is Padmini Gopalakrishnan and I work at Xilinx. Today I'll be talking about techniques to accelerate design closure in FPGAs. So, multi-million gate designs are possible today primarily because of advances in electronic design automation. What this basically means is that designers design their functionality at a higher level of abstraction, and then tools are used to implement the design to produce an optimal solution that satisfies the designer's constraints. The objective of this talk is to give you all an overview of the challenges involved in implementing designs on FPGAs using these automated tools, and also give you a flavor of some popular solutions or methodologies that are used to accelerate design closure. So the outline of my talk is as follows. I'll start by giving a brief overview of the hardware design process, take you through what is design closure. Then we'll understand the steps in a typical FPGA design flow and look at both estimation and optimization techniques that are used to accelerate design closure. So one key thing to remember when designing hardware is that hardware is concurrent by nature and sensitive to real time. This is somewhat different from software, which tends to be sequential. So as a result of this, a description of hardware tends to happen in a concurrent programming language. So the category of languages used to describe hardware are called HDLs, or hardware description languages. Some popular examples are Verilog, VHDL, and System Verilog. Now the goal of the hardware design process is basically to describe the functionality of a design and then implement it on an FPGA subject to constraints which are defined by the system or the user. A description of a design at a higher level of abstraction is basically in a hardware description language. This can be used to define both sequential behavior, which means memory or storage, and combinational behavior, which means processing functions. The descriptions in a hardware description language can be both simulatable, which means that the behavior can actually be simulated using software, as well as synthesizable, which basically means that the description in the HDL can be compiled into hardware using the appropriate EDA tools. Now, a very important part of the entire design process are the constraints. These constraints are typically specified due to the system that is being implemented. And some of the different kinds of constraints are as follows. So the first is timing. This tells you whether your design will work correctly and at the specified speed that suits your protocol or your application. Then area. This is typically dictated by cost. So the area constraint basically tells you whether your design will fit within the area budget. And if it does fit, whether there are enough resources to route the connections in the design. Finally, there is power. So typically a power budget comes from the system and the amount of cooling that is available. And the power budget basically determines whether the design will actually run at the power available. So in any hardware design today, there is actually a spectrum of hardware choices that are available to the designer on which to implement their design. So the picture on this slide actually shows the entire gamut of choices based on programmability and performance. So we have some different categories of designs. So first there are microprocessors like those from Intel or ARM. Then GPUs from companies like NVIDIA, ASSPs, which are chips from some examples are chips from Broadcom or Qualcomm, which are used to implement typically communications or signal processing type of protocols. These are basically chips which are targeted to a certain application, but are programmable to a certain class of applications, but are programmable by writing software. Then we have SoCs, which have a processing unit, which is programmable by writing software, as well as a programmable logic array in which the hardware can also be programmed. Then we have FPGAs, which are gate arrays consisting of programmable logic elements. And finally, we have ASICs or SoCs, which are completely customized for a given application. Now, what's interesting is that as you increase the amount of customization, you actually can get a higher performance and a lower power and area. And the reason is that you implement just those pieces which are required for your application to work. However, customization is costly, and with increasing masks and fabrication costs, it is getting very, very expensive. So applications actually need a really high volume to justify the manufacturing cost involved. Now, on the left side of the spectrum, you see designs which are more programmable. That is, the hardware platform is generic, and it can be programmed either through software or hardware or a combination of both. So something like a microprocessor is extremely programmable. You don't have to, you can implement any application by just writing a program, but it gives you much lower performance as well as higher power and area compared to a completely custom application. Now, as the more programmable an application, the more programmable a hardware platform, the easier it is to actually amortize the manufacturing cost over volume. So in this talk, we'll focus on FPGAs. But before going further, I would like to actually also, delve a little bit into the differences between an FPGA and a completely custom chip for an application or an ASIC. Right? So an FPGA, as its name suggests, is a prefabricated array of programmable logic elements and interconnect tiles. And the functions in the logic blocks and the connectivity between them is completely programmable. So these chips are prefabricated and the functionality is programmed into them at runtime. For a completely custom chip, however, it is specifically fabricated for an application. Typically, this is done using very primitive logic functions like ANDs, ORs, XORs, and inverters and buffers, which are available in a standard cell library. And there are routing layers which are available to connect these logic functions. So because an ASIC is customized, design closure typically takes a very, very long time, running into months. And because an FPGA is programmable, a lot of margin is actually built in to make it easy to, run a spectrum of applications on the chip. And so this allows the time taken to close on a design to be narrowed down into weeks. So here is a picture of a typical FPGA. This is not drawn to scale. So you can see, a grid of logic elements shown in dark blue. You also see interspersed between the logic elements arrays of different types of blocks. These are shown in different colors. Now these blocks are of different types. So modern FPGA devices are extremely complex. The earliest ones just consisted of arrays of lookup tables which could implement almost any function. But FPGAs today consist of a variety of logic elements including I/O, serializer, deserializer elements or SERDES, lookup tables to implement core logic, memory in the form of block RAM devices, registers, and flops, DSP and arithmetic blocks which are specialized to do arithmetic operations like carry, accumulation, and multiplication, and then clocking modules such as PLLs, phase locked loops, and clock dividers and multipliers. So a typical design FPGA design flow is shown in this slide. So a customer starts with their system level design at an abstract level in an HDL language, along with constraints for the design. So these constraints may be coming from the cost of the system. They may be coming from the board on which this FPGA chip has to be put. And they typically define the speed at which the system should run, the area of the design, the power of the design, and so on. So the customer starts with their HDL design and then they run through behavioral simulation to check if the behavior of the design actually matches an expected specification. Now, during this process, the customer might find bugs. They may decide to, sometimes they also iterate through the design by having different teams build different blocks. Sometimes they may add new features at later phases. So all this means that there is a constant loop between HDL design and behavioral simulation with many changes to the HDL and the constraints coming in the process. Once the customer has a reasonably frozen description in the HDL, they would then go into FPGA implementation. Now what this means is you actually take your HDL and using EDA tools, you actually come out with a placed and routed implementation of this design on the device. Following this, typically one would run static timing analysis to see if the design meets its performance constraints. And then after that, a bit stream would be generated for the design and it would be loaded onto the board, onto the FPGA, which is on a board. And then further simulations would be run to validate the design. Now the entire design flow is actually a complicated set of steps because the design is constantly changing and many teams actually continue to refine the HDL design while at the same time trying to make sure that it can be implemented within the constraints. So this means that there are several loops to actually that result in HDL changes and constraint changes through this process. So the time design closure is basically the time taken to take a customer design in HDL and get it to the point where it works on the board. In this talk, we will actually focus on a very key part of this process, and that is the step that takes an HDL design and generates a placed and routed solution that meets the constraints. Now this step is a very critical step to the entire closure of the design. And designers typically want to be able to do 4 to 6 turns of this step and preferably of the entire flow in a day. So the typical FPGA implementation flow is shown in this diagram. So we start with the customer HDL design and constraints as an input. This is followed by a step called synthesis, where the HDL is essentially compiled into a netlist of primitive blocks. So a netlist is nothing but a logical description of a set of logic elements which are connected by wires. The logic elements could be combinational elements that do processing, or flip-flops that actually store value ones and zeros and behave like memory. Synthesis is followed by placement, which basically involves assigning and packing the primitives in the HDL netlist, in the netlist after synthesis, sorry, and assigning them to legal locations on the device. Now, there may be iterations between placement and synthesis until the designer feels that the result is satisfactory enough to take the next step. The next step after placement is called physical synthesis. This typically involves placement or logic changes to the netlist to improve timing, area, or routability. And once again, there may be several iterations between physical synthesis and the place solution before proceeding to the next step. The next step is called routing. This involves generating the interconnections between the elements that are placed on the FPGA based on the connectivity in the netlist. And once again, there are typically several iterations between routing and physical synthesis, and sometimes even placement, to make sure that the design meets all the constraints given by the user. Finally, once a routing solution has been obtained, static timing analysis is run to measure the performance of the design and sign off on the timing. So this entire process of closing on the design implementation has many challenges. The main thing is that each step shown in the previous slide is actually a very complex and constrained optimization problem with multiple objectives. So the design needs to meet the timing constraints given by the user. The design needs to be routable. The design needs to fit within the chip, and its power needs to fit within the power budget. What makes the problem very interesting is the fact that these objectives are actually not independent, and they have to be traded off against each other to get an appropriate solution. Furthermore, the cost function is not continuous. It is actually discrete, and so not all solutions could be legal. Right? So the solution space also is very complex. It's not a smooth, the objective function is not smooth. So it consists, the objective function typically has a large number of local minima in which the optimization could get stuck. And good algorithms and good tool methodologies actually involve the usage of separate steps to climb out of these local minima to get to a more optimal solution. I'll just take a step back here to introduce what are meant by timing constraints on a design. So typically any design in an FPGA consists of a number of paths. So a path is defined as something that goes from either an input or output or a flop through combinational logic to another flop or input and output. And a flop is nothing but an element that registers the value on its input on the edge of a clock signal which is given to it. So basically there are several constraints that define the clock period or how fast the design runs. The data must reach the capture flop. So once it is launched by the first flop, data must reach the capture flop before the next clock edge arrives. And it must be held for long enough until the flop can actually capture the value and store it. So the frequency at which the design runs is basically determined by the worst path in the design. This path is called the critical path. And this is the path which is furthest away from satisfying its constraints. And designs typically have many clocks, tens of clocks, and very complex constraints that specify the relationship between the data and the different clocks on the design. Delays coming into the chip from the system level are also modeled through constraints. So the implementation design closure process is actually, as I mentioned, a very complex one. What's very important to users or designers is that they would like to do multiple turns in a day. Bear in mind that these are designs that typically have hundreds of thousands and in some cases even millions of logic gates. And designers typically would like to do 4 to 6 turns in a day so that you can actually be productive. So this means that EDA tools must obtain a solution of one pass through this flow with reasonable runtime and memory. So another challenge in this entire process is that of measuring the cost function accurately. While one tries to optimize area during the synthesis step, the actual area is really known accurately only after placement and packing is done. While one tries to optimize timing during the synthesis, placement, physical synthesis, and routing steps, the timing is actually accurately known only after the entire design has been placed and routed. Similarly, when one goes through the entire flow trying to make sure that congestion, which is an estimate of routability, is reasonable. But whether the design actually routes or not will be known accurately only after routing. So so through this flow, one makes a large number of optimization moves. Right? So another challenge is that moves which are made at earlier steps in the flow obviously have a greater impact because they determine the trajectory of the optimization in subsequent steps. Right? However, moves made early in the flow are less accurate because the cost function is less accurate. So moves are actually more accurate later in the flow, but relatively expensive to backtrack if we get to a bad solution. So this means that during the process of implementing an HDL design on an FPGA, estimation and optimization must go hand in hand. So to accelerate design closure, basically EDA algorithms focus on reducing the runtime of one iteration through this flow. And there are several ways to do this. One is to improve estimation accuracy. So earlier in the flow, such as in synthesis and during the early stages of placement, fidelity is more important. That is, one needs to be able to distinguish a good optimization move from a bad optimization move. Accuracy becomes more important later in the flow, where you may actually need to determine how good your move is. The other thing that could be done to improve runtime is to improve algorithms so that you can make better global moves earlier in the flow. One also needs to find the right place in the flow for a given optimization algorithm or targeting a given objective. And this is once again tied to estimation accuracy. So there is, given that your estimates of timing and area and congestion are very inaccurate in the synthesis phase, there is no point in running an optimization algorithm there if it cannot give you a gain which is higher than your error in estimation. And this is true at all phases in the flow. So a very important part of designing an EDA tool flow is actually figuring out which optimization must be called when. The other way that designers like to accelerate closure is by reducing the total number of iterations through this flow. Today, most hardware companies actually try to define a methodology to do this based on their understanding of the device architecture and the tool limitations. The holy grail, of course, is to do this automatically, but that's a very open question right now. So let's look at estimating timing at different stages in the flow. As I mentioned earlier, estimation and optimization go hand in hand, and a good estimation is actually key to having fast design closure. So during the synthesis phase, delays are estimated typically using levels of logic early in the flow. So for example, if you take a look at this netlist which is shown here, the path going from input A to output O1 actually goes through two levels of logic, this gate and this flop. The path going from input A to output O2 goes through four levels of logic, three gates and a flop. So therefore, the path from A to O2 actually incurs higher delay than the path from A to O1. So this metric is typically used in synthesis to distinguish between a move which is good for timing and a move which is bad for timing. So moves which are good for timing would typically ensure that the worst case levels of logic on a path are bounded. Synthesis tools also use wire load models which are usually based on fan out. Fan out is nothing but the number of loads that a gate is connected to. So for example, this gate here is connected to two loads. Right? And the higher the fan out, typically the higher the delay. There are also some wire load models that will try to make a guess of what the placement might be based on the size of the logical hierarchy in which an instance or a net is found, and so on. These estimates are fairly inaccurate, and so at this stage, basically, fidelity or the ability to distinguish a good move from a bad move is more important than an accurate estimate of delay. The next step in the flow is the placement step. So this typically involves two stages. One is global placement, which produces an illegal solution that optimizes a real cost function. And typically this starts with coarser coordinates which get refined more gradually. The next phase is a detailed placement step which legalizes the global solution found in the previous step. And this results in more fine-grained and legal coordinates. Right? So since placement occurs in a series of steps, the estimates of delay can actually go from coarse to more accurate as the coordinates get more accurate. So adjustments are made for various factors such as the fan out or even the location of the net on the device. So the picture here shows a driver driving 3 loads, and you can see that for the given locations one can draw a rectangle that completely bounds the driver and the loads. This rectangle is called the bounding box, and a very coarse estimate of the length of this net that connects the driver to the loads can be given by the half perimeter wire length, which is basically the sum of the two sides shown by arrows of the bounding box. So this estimate is basically used early in the placement flow. As the placement coordinates become more fine-grained, one might actually use a tree to try to estimate what the routing topology of this net might look like. And through this process, adjustments are made for various characteristics of the device. So sometimes delay could vary depending on exactly which part of the device instances are placed in. And of course, there are variations based on fan out as mentioned earlier. Next, we move to congestion. So congestion basically is a way to estimate whether a design can be easily routed or not. Very simply put, congestion is really a ratio of the demand for routing resources divided by the supply of the routing resources. So synthesis typically uses very, very coarse estimates for congestion because it's very dependent on placement information. So the kind of estimates used in synthesis would be the density of pins on clusters of cells. So where logic is very compact and there are a large number of pins, it can be hard to actually find routing resources to route to all the pins. During placement, congestion estimation becomes more accurate. So here there are typically two types of congestion. One is global congestion, which correlates very well with the total half perimeter wire length of all the nets in the design. Local hotspots are actually harder to predict. Because of this correlation, you'll find that practically every placer will actually try to make sure that it optimizes the half perimeter wire length of all the nets in some way. Now, modern placement tools also use a probabilistic model to estimate congestion. The way this probabilistic model would work is as follows. So if you see, the figure below shows a net enclosed by its bounding box, right? And while here we show a specific topology of a tree, there are actually many possible topologies, and each topology would use a slightly different routing resource within that bounding box. So essentially, you can come up with the probability of a given routing resource being used by a net by taking different possible topologies inside this bounding box. And that probability is basically summed up over all nets and used to estimate the congestion on the design. A very important point to note is that trade-offs basically make the optimization problem very complex. And so, for example, in synthesis, reducing the levels of logic on the critical path can actually increase area on other paths. Now, increasing area makes the placement problem more complex. It makes it harder to optimize wire length and therefore congestion. It can also sometimes make it harder to meet timing if synthesis has not accurately estimated which path is critical. The other trade-off in synthesis is that packing logic densely together to improve area can actually increase pin density, making it harder to route the design. Now, during placement, we would like to place parts physically close together to improve timing, but this can actually cause contention for pins and routing resources, and therefore increase the congestion on the design and make it harder to route. So as tools take a design through the different stages in this flow, they're constantly making trade-offs in the different algorithms used. So ideally, automatically optimizing the entire design is ideal, right? You would just like to push a button, feed in an HDL design and constraints to a tool, and have it produce a placed and routed netlist that meets all your constraints without any intervention. However, in reality, designers actually need to make changes to the flow, by tweaking knobs or parameters based on the design and the constraints. And because of this, feedback at every stage from the optimization engine is critical. And this is actually a very key factor that determines the successful adoption of an EDA tool flow. So some examples of the kind of feedback that would be given to the user could be, how many logic levels are seen after synthesis on different parts. After placement, the user might want to actually look at how critical parts are placed to see if there is, scope for improvement, or if synthesis changes such as replicating certain pieces of logic need to be done in order to make sure that the parts can be placed more compactly. We may want to check if there are detours after routing. That's typically an indication of congestion in the design. Another important piece of feedback is whether there is actually correlation between the estimated and actual delays and congestion. This could tell you whether further optimization is needed in the algorithms to actually, or if there is a bug in the tool that is preventing the design from being closed. So to summarize, designing hardware on an FPGA involves describing a function and implementing it on an FPGA to satisfy constraints that come from the user or the system. A key step in closing on the entire design cycle is basically taking an HDL description of the design to a placed and routed solution that satisfies the user constraints. And this is a complex multi-objective, multi-constrained optimization problem. One can actually compute the cost function accurately only after the design is routed. And it's very important to enable multiple turns of this design flow in a day to allow users to be productive. Finally, design implementation closure depends heavily on both estimation and optimization. Multiple iterations through different phases in the flow are required, often with some manual intervention. Moves made early in the flow have global impact but less accurate cost evaluation, while moves made later in the flow are more accurate, but they tend to be local in scope because it's so expensive to backtrack and make a big change. This brings me to the end of my talk. I'd like to thank Global Tech Women and Xilinx for giving me the opportunity to make this presentation. Thank you.